All right, so previously we obtained the magnitude, right, for this transfer function from this complex number here, complex rectangular form representation of the transfer function, V out over Vs. Now we're going to do the same for the phase, so let's just copy this and take it on over here with us. Throw it up here. And so we know that the phase, or the angle of V out over Vs, is equal to the tan inverse of the real part, which in this case is going to be R over omega L divided by, I'm just going to say denominator. I hope you guys can see that those two denominators are equal. I'm just going to call it the denominator because it cancels to save us some time. And so I can just say that these two denominators cancel, and I get that the angle of V out over Vs is equal to the tan inverse of R over omega L, or the tan inverse of R over 2 pi F L. All right, so draw a box around that. And of course, I'm just saying that this term here is called the denominator, DEN, because they're equal. I just didn't feel like writing them out again. All right, so yeah, I knew that was going to happen. I just wanted to move this down a little. Okay. All right, good. So we've got the phase here in terms of F, right? We've got the magnitude over here in terms of F, so let's grab this. Copy and paste it over here. And of course, this is my phase in terms of F. This is my magnitude in terms of F. And now we can come to the next slide where we're going to go ahead and plot our magnitude and our phase like we did previously. So let's grab this one. Oh, I guess I never erased these. I recorded this once and my video got messed up. So that's great. I already have them. So I'll just leave them over there. So we're here. I created these two plots, and it just so happens that the value for the magnitude is going to vary between 0 and 1, just like it did previously. So I'll put 1 here, I'll put 0.5 here, 0.75 and 0.25. And then for the phase, in this case, it's a little bit different. It's going to vary between 0 and 90. Okay, so instead of going negative this time, it's going to be 90, we'll go 67, 45, 22, and 0, of course. All right, and again, these are both functions of frequency F, and we'll look at the same data points that we looked at last time. So we'll look at 1, 10, 100, 1,000, 10,000. And then I threw 300 in here, which was right here. And so let's grab those. And let's also look at those for the phase. And I'll go ahead and end this video here now that this is all set up. And then in the next video, we'll go ahead and plot the magnitude response and the phase response for the RL circuit, okay? Again, we're just looking at an RL circuit here. And we are plotting the output versus the ratio of the output to the input for this particular circuit as we vary the frequency of this input source. Again, the inductor is an impedance that changes with frequency, and so things happen over spans of frequencies where the magnitude of the output changes because this impedance is constantly changing, okay? Well, not constantly changing, but changing as we change frequency. All right, so let's end this video here, and in the next one, we'll go ahead and do these plots.